Um, all right, thank you all for coming. Hello. For those of you that don't know me, my name is Ben Pfeffer, and I'm talking about my capstone today. So it's generating cancer images to improve cancer diagnosis accuracies. So what is the problem we're trying to deal with? Well, we know that the earlier cancer gets caught, the more likely a patient is to beat it. So early diagnosis of cancer is crucial to a patient's survival, which is why the second bullet point is scary, that up to 28% of cancer cases are misdiagnosed. This number is difficult to estimate since there's a difficulty in reporting it, but it tells us that there's plenty of room for improvement in this field. So when we go to a doctor, we can trust that the information we provide them will remain confidential. And the reason we can do so is because of laws like HIPAA, which require doctors to keep that information confidential unless patient consent is given. But because of that law, there's a lack of publicly available medical data for us to use to improve AI in the medical field, which causes a lagging of AI in that field. So we need more data. And in the last decade, this idea of generative adversarial networks has come around, or GANs, and how they work are they generate novel images from existing ones. So the idea here is that we want to generate more cancer images to improve the diagnosis accuracies and abilities of a deep learning model. So the image data we'll be using today is breast cancer images, and we'll be using an ordinal label since we're, for the category we're classifying, we'll be using the immunohistochemical H score, which is a 0 to 3 score of 0 meaning there's no cancer, 1 meaning there's a little bit, 2 a little bit more, and 3 the most amount of cancer. So because we have those two factors, we want to be using an ordinal convolutional neural network to classify our cancer cases. So the architecture of this process is shown here. So first we want to obviously gather our data and pre-process it. And then we want to use our GAN to generate more data, which we would then use to augment the data set. And then we want to train two models. The first would be on the base data, and the second would be on the augmented data set. And then we use both these models to predict on identical test sets and compare the results of that prediction. So first, the fun part, the data collection and pre-processing. So where would we get this data? Well, luckily for us, Stanford's tissue microarray database, or the TMA database, contains thousands of images, and in those images, there are many different types of cancer. Specifically for us, we're looking at breast cancer. So we scraped 665 breast cancer images and their corresponding H scores to use in this process. And those images looked like this. So you see a very high dimensional cancer image of 1504 by 1400 pixels. And for at least this project, this is far too high dimensional to use. I wanted something more in the range of 64 by 64 image. So the easy way to do this would be to just downsize the image, which we could do. But then, no, you're not going blind. This is actually how terrible that result is. We lose most of that information that tells us whether or not there's cancer in the image. So we want a way to reduce the dimensions of the data while maintaining that core relational structure of the pixels that tell us if there's cancer. So the way we chose to do this was to use a gray level co-occurrence matrix, or a GLCM. And how they work is you first convert an image to grayscale, and then you select a direction and distance away from 2 pixels, and take those values at the beginning and end and use them as X and Y values, and then create a heat map as you do this process for every pixel in an image. And then we can bin them into 64 by 64 axes. And you see what we have here, a 0, 1, 2, and 3 score of your cancer images converted to a GLCM. And this is beneficial because it allows us to reduce the dimensions while maintaining that structure of the cancer data more clearly, but also because if we look here, these two cancer images on the left are H score of 3, meaning there's the most cancer. But when we convert them to a GLCM, they are much more similar, which is what we want, because when an AI model or deep learning model tries to classify these two as the same, it's theoretically more difficult than when it tries to classify those two as the same image, or as the same category, I should say. So that's the other reason that using GLCMs is beneficial here. So now we get to the data generation and augmentation and the GAN. So I decided to use a deep convolutional GAN, or a DC GAN, and GANs work by there being an adversarial network. So there's a generator and a discriminator working against each other to generate an image. The generator will come up with an array of pixels, and the discriminator will determine the difference between the generated images and the real images and convey that information back to the generator. And this process repeats itself over and over again, resulting in, over time, better images of that cancer data that we need. So through this process, we have two images here. I want you guys to think for a second which one of these might be a generated image. For those of you that think it's the one on the left here, you're wrong. Those of you that think it's the one on the right, you're also wrong. I just want to make sure you guys are paying attention. So one of these is actually generated. Take a minute to decide which one that might be. The generated image is the one on the left here. It was basically a 50-50 shot in my eyes, at least as I see it. The point here is that the images are basically indistinguishable from those input images, which is what we want. So then now that we had these generated images, we could augment the data set, and we followed this process you see here. We want to duplicate our data set, maintain that train test split, then augment the training set of the base data set with those augmented images or those generated images so that we had two data sets. And now that we had two data sets, we could then move to the model training and prediction. So as mentioned before, we're using ordinal convolutional neural networks. So for one of the models, we send in the baseline training set for it to train on, resulting in what we call the baseline model. And for the other one, we send in the augmented training set into the ordinal convolutional neural network to train on, resulting in what we call the enhanced model. And then we had two models. And now we could compare the results. So we wanted to use these to predict on identical test sets, which we did. And we scored these images and repeated the last half of those steps 100 times to ensure that the results are valid. And then we compare the results. So we're looking at accuracy first, as we want to compare to previous uses of this data that looked at accuracy. But also we want to look at MAE and MSE, because error values in this kind of scenario are important. Because, for example, if someone is diagnosed or should be diagnosed with a score of a 3, but they are diagnosed with a score of a 2 versus a 0, accuracy would categorize those both as the same thing. But error allows us to determine that 0 is much worse than that 2, because that 0 allows a patient to go home, continue their life, and allow their cancer to get worse, which is bad, obviously. But the 2 score allows them to begin treatment and hopefully begin getting better. And then also here we look at convergence of the two models as well to compare them. So what do we find? Well, first, looking at these 3 box plots here, we see, well, in each of the box plots on the left, we have the enhanced model, and on the right, we have the baseline model. In the enhanced model for accuracy, MAE, and MSE, we see an improvement in the enhanced model for all metrics. And these can be summarized in that table in the bottom right there. We use the median value for those tables, or for that table. We can see the enhanced model has an accuracy 82% compared to the baseline model's accuracy of 76.8%. And I'll let you guys read those other numbers as well. But in all cases, the enhanced model outperformed the baseline model. Then, if we want to analyze the convergent traits of these models, for the blue model here is the enhanced model, and the red model is the baseline model. And we can see with a reference line of 0.25 that that enhanced model converges to that reference point much quicker than about half as quick or twice as quick as the baseline model, and that baseline model continues to bounce off of that line and stay above it, whereas the enhanced model continues to fall below it over time. And you might also notice here spikes along that graph, mainly in the baseline model, which tell us that the enhanced model is much more stable in its training over time. And we can see similar things here. So this is for MAE. We can also see the same thing for MSE, or a similar thing for MSE as well. And then if we want to look at example results. So this is the, well, I should explain it first. The actual value is on the x-axis here. So when the actual value is 0, we have these results of prediction values of 0, 1, 2, and 3. And when it's 1, we have those results 2, and so on. And when we use a GAN, we can see improvements in that. So we see that looking at zeros first, with a GAN, we have 115 zeros predicted correctly, since we want to see only greens in that first section. And we can see a lot of those were moved to that. Were moved to that 0 category. And second, if we look at the ones, we can see that all 5 cases were predicted incorrectly first, but then when we used that enhanced model, they predicted correctly. And then 2s, it was not great at predicting in either model. But we see that using the baseline model, it predicted 14 out of the 15 cases as a 0. But the enhanced model sends 5 of those people as having some semblance of cancer, which if this were actually used, would help them out significantly. And then the last value, we see improvements in the 3s as well over there, in a similar way we've seen earlier. So a few takeaways from this. We know that we've seen that GANs can be useful for data augmentation on small data image classification problems like this. But we also have seen that AI on cancer image data specifically can be improved when we use a GAN to augment the data set, as we've seen through the accuracy, MSE and MAE metrics that we've looked at. And then finally, as we saw with the convergence plots, that GANs may improve the overall training time of your model, given that your model isn't like a quick model to train. It takes a good amount of time. GANs may improve that training time. So is this idea viable for general use? Well, potentially, obviously not right now, but we want to look at this idea used on larger data sets, first of all, but also using different GANs, like perhaps NVIDIA's style GAN, which to my understanding is a state-of-the-art GAN that is better at dealing with high resolution images. We want to look at data sets outside the medical field as well to see if they can be used outside the medical field. And finally, we want to look at larger images. Since I only used a CPU for this project, but if you used a GPU, we could look at larger images and see how well it performs with larger images. I'd like to acknowledge my advisor and mentor for this project, Professor Dong Yan. He's not here today. I don't see him. But it's his idea for this project, and he's helped me a lot along the way. So thank you to Dong Yan. Thank you. Any questions?
Hi, I have a few questions. So firstly, did you use, what kind of GAN did you use?
It was a DC GAN, a deep convolutional GAN.
Okay. Was it something off the shelf, so to speak?
Sorry, repeat that.
Off the shelf, something that TensorFlow, for example.
Something that, sorry, repeat the last part again. Something that what?
TensorFlow, something that is stock ready.
Oh yes, it was used in, it was created in PyTorch. It has been created before. Yeah.
Okay. Why did you not use confusion matrices when comparing test results?
Yeah, I could have used confusion matrix. I like that view of the bar graph better. It was just a personal choice I chose to use.
Okay. And could you go back to the images that you tested us with?
Yeah, sure. Pull back up. Where's that? Here. So this is the one on the left here is generated.
Right. When you're looking at these two images in the intense orange regions, you can see blobs that are situated differently on the generated image and the real image. Is that a potential concern, especially when one deals with cancer?
Yeah, it could be. That's why it's important to look at this with a better GAN. Like a DC GAN isn't really state of the art. That's why I mentioned style GAN at the end, which to my understanding is better able to generate more realistic images. I thought this was close enough. This is why I continued using it.
And final question, you said that you're using CNN for the actual cancer recognition. Is it again off the shelf CNN or something that you designed yourself?
So it's off the shelf, but it's not a normal CNN. It uses this layer called a coral layer, which is consistent ranked logits. It takes it's a way to take the output and add linear bias into the predictions and make them ordinal.
Did you say winner bias?
Linear, sorry.
Linear. Okay. Thank you.
Any other questions? Very good talk then. So just have questions when you extend this data with the GAN, right? So you overpopulate it with extra data.
Yeah.
So it seems like to stabilize the training before you have some spiky training. But how far you can extend it? Like for example, if you overpopulate the data with let's say 80% of the fake, right? So do you think it's gonna harm the training, or because the doctor may not have to say, okay, sorry, doc, these data are fake, and after they keep analyzing, right? Like,
yeah, I mean maybe.
So how far you can extend this I mean, like, if there's any study about it.
I haven't seen it. Yeah, maybe I haven't seen any study on that. I would say it could be extended to the point where you don't have more generated images than real images. That's where I put the limit at, but that's not research at all. That's just assuming what's best for it. All right, let's take a